Okay, well, good afternoon, and thank you very much for the invitation. I'm going to share with you some of the work we have done in this whole field of big data and machine learning, and I'll give you a couple of examples. There are many, many people to thank for this work, including one of our collaborators, Ellen, here with some of the work that I'm going to talk. First, I'm going to give you motivation. Going to apply it to a forward problem using large-scale simulations, learning from field observations, inverse problems. And I'll have two examples, vertical arrays and urban excavations, and then some concluding remarks. So what's the motivation? The motivation is nowadays we're able to do ever larger, bigger, massive simulations. And then the idea of asking our students to get the data, put it in an Excel sheet and come up with some correlation is really not viable. You've seen the machines here. We actually use them extensively. We're able to generate very large data sets. What can we do with this data set to be able to develop reliable risk-based design and models? We'll talk a little bit about that. We're acquiring large data sets from the field, and are we using that data to improve our knowledge, to improve our understanding of the fundamentals of material behavior? And I'm going to talk a lot about simulation. We have centrifuge experiments, instrumented buildings. We're looking at using smartphones, terabytes and petabytes of data. What do we do with this? And so let me give you some examples. So the first one is large-scale simulations. This one is motivated by trying to characterize the side effects for earthquake problems, the impacts of sites on our ground motion. And if you're doing a regional study to incorporate the information in a hazard map, you need to incorporate many, many different realizations and then come up with amplification models. So we have been doing, as part of the NGA East Geotechnical Working Group, large-scale simulations, and we generate a lot of data. And we developed a number of conventional, let's call them amplification models that are used in the seismic hazard maps, but we found that they are limited in that they still carry with them large errors. And we have options of how do we proceed with that. You can add parameters, enhance uncertainty characterization, but that may not be enough. So we need to do something else different than our conventional way of building our models. The simulation study is very large, the one we have dealt with to incorporate ground motion effects, soil profiles, material properties, depth to rock, and that resulted in a simulation in 1.7 million simulations. We're doing a more recent, newer study now with 3.6 million simulations, and then the output from those is 30, 40 million, and we have 5 terabytes of data. The first set we have 2.5, now we're 6 terabytes, and we put this in a data set. So how do we use that data set in characterizing site effects? We call this thing called the amplification factor. You take the ground motion intensity measure at the surface, divided by some input rock, and that embeds, shall we say, the effect of the soil column on your ground motion. And there are linear and nonlinear components. The functional forms, this is just to give you an idea about the complexity of these. The functional form is usually the amplification factor. We put it as a function of shear wave velocity. We call it VS30. This is the slowness parameter of the soil column in the top 30 meters. And we develop these functional forms for it. And then we can add other terms such as the natural period of the soil column to enhance that prediction. The nonlinear form also becomes also complicated. There are many terms that you have to bring in to be able to incorporate the soil nonlinearity into your model. And we have published this work on these results. The measure of a model is you see how well it fits the data it is used to represent. This is a graphic showing you the residuals, and a good model, you want the residuals to be centered on 0, right? And you can see that in certain parts of the shear wave velocity spectrum, we are really not centered around zero. So what do we do? Do we add more model coefficients to better match the data? This becomes really unwieldy, very difficult to do, and it's not easy to understand and figure out exactly how I can improve my model. Well, so what did we do? We decided instead of using conventional functional forms, we used neural networks. The input to the model is exactly the same as any other conventional input we use in our site amplification. Why? Because we want this to ultimately be used by the community, which is in the community of seismic hazard mapping, and we do not want to change the input funnel. Inside, there is I think yesterday in the workshop, you probably had a bit of an idea about what a neural network, and then the output is also what they are used to. The input is the same, the output is the same. It's just the inside we don't know exactly the functional form in a traditional sense. And I always say, and do we really care? So we're able to have such a flexible framework or functionality to capture the data. And so what we did is then we trained it on the same data set that we used to regress the conventional models, the exact same data set, exact same thing. And we are actually doing a much better job in terms of capturing the trend and the width of the trend. And then if we look at our residuals now, compared to those of the conventional functional forms, they are centered on zero. And also the band, the sigma, is smaller, by the way. So this means you have a smaller error. And if we look at it in a root mean square error, and this is for the linear function and the linear amplification and the total amplification, we have somewhere around 30% reduction of error. Now, why is that important? This is 30% in log scale, by the way. So from an engineering point of view, this reduction in error is massive. It's hugely important for us because it's giving us a far more reliable functional form to use for site amplification. So it's an example of how we apply artificial neural networks, large data set simulation data, and put them all together to be able to improve our models that are used in engineering applications. The artificial neural network work is still in progress. We haven't deployed it yet, and we'll have to convince the USGS to ultimately use it as they did our previous models. But the error, you really cannot argue with the reduction in the error there. Now, why do we care about these things? Because we're going for ever larger simulations. This is a large-scale simulation that we are currently working on with one of my PhD students, whereby we're looking at the interaction of tall buildings with tunnels, underground structures. And we want to build three-dimensional models because we want to do 2- or 3-dimensional shaking. And there we're, if you're interested, this is LS-DYNA, and we're running it here on these machines. We're going to have around 59,000 simulations. And if you know about finite element modeling, you have X number of nodes, X number of material points, integration points. So we're going to have a very, very large data set, and we plan to use artificial neural networks to be able to do our evaluation of these results. And ultimately, in how you carry that through in terms of your risk calculation, there's another project I'm involved with where we are trying to do that, and these tools will be very handy. Okay, now I'm going to switch to another problem, which is, first is the forward problem. I'll give you an example of an inverse problem, learning from observations. It's an inverse problem. This is self-learning simulation. This is a technique we have developed at the University of Illinois for quite a few years. And the way you want to think about it is, how can I develop a large data set from limited field observations? You see, our field observations, especially, say, I'm going to take the earthquake problem, are always limited. We have a few points here and there, but how can I get something more out of that data by bringing in other considerations? So we have an input and we have an output, and we do not know the guts of it, you know, the mechanics of the problem. That's the unknown for us. If that system behavior could be material behavior, laboratory exam, sample, deep excavation, vertical arrays. So the way we do this is the way we often do our modeling is we have a finite element model, we have a mesh, and we have a material model, right? A material constitutive model, linear elastic, nonlinear hysteretic model. Now, we have a force and we have a displacement. We have our constitutive model. It's often, it's actually for, especially in, for geotechnical engineers, that's the unknown quantity. And instead of using a conventional hyperbolic constitutive law or a bounding surface plasticity model, I'm going to propose that we're going to use a neural network-based material model, okay? Not a conventional material model. Why? Because if you look at our literature, the constitutive models out there are a dime a dozen. I have contributed my fair share to those models out there as well. But if you change to that, it requires a change of thinking. So let's look at how we're going to do that. So I'm going to take vertical arrays. So vertical arrays, what it is you put some sensors at the ground surface and within the soil profile, and you have a shaking event, and you are able to see the wave propagation, and you try to simulate it to understand the material behavior. Well, it is fundamentally an inverse problem. If we use our conventional models, I have a fixed form of my constitutive model, and I try to tweak it and do some ad hoc changes. We call this optimization. You run into uniqueness problems, etc. But there is more information in these models that we can do a better job extracting. So instead of running a single forward analysis with this, I'm going to suggest that I am going to do 2 simulations, right? So I have the records from all these points in the vertical array. And what I'm going to do is I'm going to first run one simulation here, and whereby I'm going to impose the base shaking. And I'm going to say there, because the forces that I'm applying are reasonably correct, then the stresses I'm getting out of it are correct. So I'm going to take these. The strains may not be. Then I'm going to do another analysis, a parallel analysis, whereby I'm going to put in there all my measurements. And that is going to constrain the problem, whereby it is going to, more or less, I'm going to probably get my strain correctly. So I'm going to stipulate that I'm going to get the strain from that analysis. Stress, strain, that's a constitutive model. That's a material constitutive model. It relates stresses to strain. So what I do is I take that data, but how can I use that? How can I incorporate it? Instead of using a conventional material model, I use a neural network model. From these 2 analyses, I train my neural network soil material model, and I repeat the process. I keep on repeating. I start from something like similar to a linear elastic, and I let it evolve, and then I repeat that, and I repeat it for all the time steps, etc. You can see it can be computationally a bit demanding until the 2 analyses converge, and then I can say I have extracted out of that information, the measurements, enough knowledge that would be sufficient to tell me something reasonable about the material behavior. For your information, by the way, we've applied this to multiple problems, structural engineering problems, geotechnical problems, seismic and static. We've applied it to also bioengineering problems as well. And they all work really well. So there's a number of PhD theses on this. I'm just showing one example here. I'll actually show 2. So what we did is we used the Lotong array in Taiwan, got the data. Then what we did, this is the measurement, and this is our initial estimate when we started the simulation of the ground motion. This is the displacement. And we actually, when we converged, we got somewhere pretty close. If we look at our response spectrum, we matched, what we did there is we matched the analysis in one direction, shaking, and then we tried the orthogonal direction. So now that's kind of prediction, if you want to think about it. And we actually did a pretty good job. Okay, so you say, well, you've matched, you don't know what kind of material behavior. What did you get out of the material behavior? Well, we looked at our soil stress strain loops. They looked reasonable, but let me show you something more. We started looking at what kind of modulus reduction versus damping curves. This is a classic way of looking at material behavior that we use in site response analysis? Well, what we found from it is that first we got reasonable modulus reduction and damping curves represent, even though we didn't use those as an input. We compare those to empirical data. But not only that, it gave us an idea about the degradation in the modulus with a repeated number of cycles, which is an interesting metric. And what we did is we then compared it to empirical data. This is called the degradation index versus number of cycles. And at that time, when we developed this work, we found that it is actually, even though people were representing it as linear, it is nonlinear. And when we were talking to some colleagues who were doing some testing, they said, well, yeah, the new data shows us it is actually nonlinear. And so it allowed us to discover new information about the material behavior, which we didn't have from field measurements. I'm going to fly quickly through another example, and this is really to show you how we can incorporate things such as LiDAR or structure from motion information to develop our finite element models and then do this inverse analysis. We did that for an excavation problem, which we used it to automatically convert to a finite element mesh, and then did our learning behavior, and we learned nonlinear behavior. Conclusions. Okay. The age of big data and machine learning is upon us, resulting in improved forward and inverse modeling, learning from observations. We need to shift our thinking, actually, think differently. There is a pressing need, in my opinion, to upgrade our toolbox and adapt available tools developed by others. Our friends in other areas have done a fantastic job. We want to learn how to just be good users of those. We need for focused and systematic shift in our undergraduate and graduate education programs to move beyond traditional approaches for interacting with data and information. We have to start them young, okay? Change their way of thinking. We're a little bit too inflexible sometimes in how we think about it, because we don't realize how embedded certain procedures are in the way we do things. Real data remains sparse and imperfect. There's a need for improved field data acquisition tools and sensors. I'm always a big believer in getting data. For geologic and geotechnical data, it's often quite limited. For large-scale 3D models, we need to keep that in mind. Thank you.
So we have some time for questions. Is Alex? We have some time for questions for our two speakers.
There are actually some questions on the chat.
Oh.
Okay.
Really? Okay.
Let's see.
Should escape from there.
I had to escape. Okay. Do I stop sharing first?
Yeah, you can.
Stop sharing. Oh, there's chat. Okay. Here we go. Should I read? Okay. It says, hello, I have a question regarding the accuracy of machine learning models. How do we determine the base error for most of the problems we handle in civil engineering, without which can we comment how good are our machine learning models doing, especially when we do not have any such accuracy parameters in other analysis method? How can we do a generic comparison? I mean, for the models based on real-time data, example, post-earthquake damage estimation using existing models versus machine learning.
10 questions.
Okay, yes, quite a few actually. That's great. Thank you, by the way, for the question. Do you want to take a stab at it, at some of these? And I mean, I'll express some thoughts on it.
Yeah, I can.
Please, come on.
I can provide some perspective from at least the use of numerical models. I mean, you generally go and perform cross-validation. I think you have to be careful always with cross-validation because many times it overestimates your error, so you have to be careful with it. But in general, that's the main tool that you have. You know, some statistical version of cross-validation, bootstrapping, jackknifing, and then it's up to you to figure out for your specific application what's the right statistic, either that's correlation coefficient or maximum error, but that really depends on how you want to use your surrogate model. So there is no global answer about what is good error and what's not good error.
Okay, just to add, I mean, this is great. I think one of the things as we move into the areas of machine learning is we want to be far more tolerant of errors. These models are actually, many of the problems in the real world are error tolerant. The analogy I always love when I was first introduced to it was when you park, when you park a car, there are many, many ways of parking a car. If you give that to a traditional model, it will always park it in the exact same position, by the way. If you give it to a neural network, it'll park it like we park it, and all of them are valid solutions. So there is this whole issue we need to be careful about, differences between accuracy and precision. So, but I think that's something we need, there will need to be an understanding of that, even though they are not precise, they are still adequate to solve our problem. So, shall I go to the next problem? Question?
Very quickly, because we need to get to
So for the neural network soil model, I actually love this question, by the way. If we obtain the model through deep learning, we don't know what the actual soil properties are. So how can we apply these models to any other site different from the one on which the neural network was trained? I get that question all the time. And I'm going to actually make a statement a little bit bold. If you really think about it, the only real material property is actually the material behavior. It's that stress strain curve, if you think about it. The material property, be it a modulus, a stiffness, or any other thing, these are, remember, these are mathematical constructs that we ourselves have introduced. It has become ingrained in us to think of them as material properties. No, they are actually idealizations that we have developed. Once you accept that, and I know for some people it make you uncomfortable, then you will realize, actually, then I'm interested in the behavior. Now, the question that the questioner is asking is, how can I use it? If you are within one same area, let's say you're in the San Francisco Bay Area working with the young Bay mud. If you learn from several sites, you will find that you can indeed use it at other sites with the Bay mud. However, if you want to go to another area like Boston Blue Clay, it wouldn't work for you. However, you may learn certain trends about, say, like I showed here, degradation that you can carry through to others, but you cannot do it in the same classical way of taking traditionally developed material constitutive models to other areas.
Thank you very much.
And thank you for the questions. We really appreciate them.